Dodger, like, it's hungry. It's more contact. He says that it was third member of the second. I ever sit in your, they're looking, I'm better with, you know, very small and limited.
Okay.
And I just have. No, I understand why. And their idea that now they're using calls like. Well, it wasn't like that. It's not. It's getting connected.
If you like slash up.
He's saying need to replace it all. Glad
No, actually, they're not right. Oh, yeah, no, that was one smaller. Just. I don't know, we probably got different. It's like one person right, and then started.
Okay, we're on page 36 in your packet.
I mean,
I guess, you can.
yeah.
Great, guys.
From last year.
So we have two more, technically two more tests to go over. And so today we're talking about alternating series tests and absolute convergence. So alternating series test, I'm gonna abbreviate it as AST. The idea is that if my rule of sequence is greater than 0, then the alternating series, -1 to the n times a to the n, and -1 to the n plus 1, a to the n, converge if both of the following conditions are met. So the -1 to the n, what is that going to do to each of the terms as I add? Yeah, it's going to change from positive to negative. So basically we're adding something, then we're subtracting something, then we're adding something, then subtracting something. So if you guys had to guess, is the restriction going to be less or more if we want to find if an alternating series is going to converge or not? The converging requirement, will it be more strict or less strict? Less, right? The idea is that we're subtracting values, so potentially series that normally would have a hard time converging could all of a sudden converge. Does that make sense? That sometimes there are going to be some series that before wouldn't converge, but because it's an alternating series, it's able to converge because we're subtracting enough values out of it. Okay, so you guys remember the nth term test? Nth term test says that if the limit as n approaches infinity of a sub z equal to 0, what would you say if that was what you got from nth term test? Being inconclusive, right? It would be where it could converge, but it could also diverge, right? Like 1 over n, right? We know 1 over n, the sequence, the series, the rule of sequence goes to 0, but it doesn't diverge. However, this for an alternating series is enough to basically allow for things to converge. So before 1 over n would not converge, but if it's part of an alternating series, it does converge. All right. And then the second condition is really something that we just have to be able to state, but in terms of finding an example of where this is where this first one passes, but not the second one, is hard to do. Okay, so I have a hard time finding a situation for us where it passes the first one, but not the second. We just have to be able to understand that there is a second condition technically. So this one, it just says that each term is getting smaller than the previous term. So yeah, it just means that my a sub n plus 1, the absolute a sub n plus 1 is less than or equal to a sub n for all n value. So here are ways to check if a sub n is decreasing. Okay, but technically, for our purposes though, we just have to be able to state this. We don't, if we can show that this is true, then we basically can know that the alternating series is going to pass, or the series will converge. So wait, but there are technically there are ways to check if the function is decreasing. We take the first derivative and see if it's negative. And then second, it's kind of obvious, especially if the first condition is true. And then we can also manipulate where a sub n, can we show that a sub n plus 1 over a sub n is less than or equal to 1? Okay. If the ratio of the two terms is less than 1, then we know that for certain, the terms are decreasing or getting smaller compared to the previous term. All right, let's look at some examples here. Okay, number one, determine the following series converge or diverge. We first can tell that this is part of an alternating series. So if it's part of an alternating series, the only condition that we have to really make pass is that limit as n approaches infinity of 1 over n is equal to 0. And we just have to make a statement that a sub n plus 1.
For the limit, you don't include the -1 to the end, or
It doesn't. Yeah, good question. The limit doesn't include the -1. It is just a rule of sequence outside of or removing the alternating component. Yeah. So basically, when you find the limit, remove the alternator and just focus on the a sub n. And really, we're not testing for the second condition. We're just stating it. So just get into the habit of knowing that technically there are two conditions. And if the problem ever asks you for both conditions, we just state it. But for our purposes, it's really only the first one that we need to actually work on. And we can just say the series converged by AST. Okay, number two is also an alternator. -1 to n plus 1 does the same effect as -1 to the n. It's just whether the first term is positive or negative, but it's not going, the n or n plus 1 is not going to influence how we approach the alternating series. All right, so we just define the limits, right? All right, what's this equal to?
1 over n.
Which is, well, does this go to 0 or? Yeah, it goes 0, right? Because we talked about how if we're ever approaching infinity, you compare degrees, right? Here, my denominator is a higher degree, so if that's the case, it's always 0, right? Are we good with that? Oops, sorry. That's all we need to say. Yeah.
Second condition, I don't really understand.
The second condition just, we basically just have to state it. It's basically just saying that each term is getting smaller. And that first term is basically giving us that property. We basically don't have to test it, we just have to state it. All right, what about number 3 here? Yeah. So what can we say?
Divergence.
By diverges by which test? Well, this is not AST anymore. This is something else. Yeah, end term test. Good. End term test just says that if the limit doesn't equal to 0, then it has no chance of converging. It must diverge. Right. It's the idea that if we're adding a bunch of terms together, each term has to, each subsequent term has to at least head towards 0. If it's not heading towards 0, then it has no chance of converging because we're adding all these numbers. It's got to get small at a certain rate. Okay, number 4. We don't see the -1 to the n+1, but let's explore that cosine n pi and see if that will give us some information here. So let's just plug in, let's just see what's happening here. If I were to plug in n = 1 into that cosine n pi, what does that give me? Wait, cosine of pi.
-1.
What if I plug in n = 2? Okay. N = 3. Yeah. So the alternator is hidden within this notation. Does that make sense? So now if it was sine would be like n/2 pi. In that case, it would be an alternator. So sometimes the alternator is hidden within a trig function. So just understand that. Yes. Which one? Number 4? 1 over n. All right. So let's go through our, basically this is, we have to agree, right, that this is the same thing as right? Are these not the same? Yes. So if this is basically number 1, right? So we can follow the same steps as this, right? Once we realize it's an alternator, there's an alternator. All we need is the positive rule of sequence. If we can show that it approaches 0, then we know that the series will converge. Good, that's right. Without an alternator, we would say that this would diverge by the nth term. Sorry, this would be, it would be inconclusive by nth term test, and then we would know that by p-series test that it would diverge. Yeah, good question. All right, number 5, it says the following is not an alternating series. Look carefully to see if you can tell why or why not. So let's say n is equal to 1. Mhm. It's always going to be positive, right? Because if I did n = 2, okay, so positive all the way through. If it was by itself, it'll be an alternator, but 2 alternators next to each other, they may cancel out. So just be careful, right? That I think the best way to handle these problems is just go through a couple of checks to see what the pattern is actually, right? Let's not make assumptions if something looks a little complicated. So really, there is no alternator, right? It's really just the n over n squared plus 1. And would the nth term test be conclusive? Be 0, right? So inconclusive nth term test. Okay, so let's think back then. What would be a test that we could use for this? Yeah, I think that's our go-to, right? We're gonna always attempt limit comparison test before we do anything with direct comparison, right? I mean, direct comparison is one of those things where if for some reason I'm not able to get limit comparison to work out, then my go-to is usually direct comparison, right? So that kind of fits that idea that, okay, we're rational above each other, and then there's obviously a relationship between my numerator and denominator. What could be my comparison partner then?
1 over n.
Okay. So it's just 1 divided by the other, right? So I'm going to take the new one divided by the partner. As long as this gives me a real number, I know that both of these will share the same behavior.
They don't, if it doesn't yield a real number, is it like opposite?
So if this doesn't give me a real number, then we got to try a different test because limit comparison test is not a good fit. But what does this give us? 1, that's a real number, right? We know 1 over n, what? Diverges. So this series must also diverge.
This doesn't exactly apply to this term, question, but will 1 over n plus anything always diverge?
Yes, because I can make an argument for direct comparison test that 1 over n plus anything is always going to be less than 1 over n. Oh, wait, 1 over n plus n. Oh, yeah, there's less than that. Most likely, but yeah, even direct comparison test is not a good fit for this.
But if you do a limit comparison.
Yeah, limit comparison test, well, we'll be able to give a strong argument for that, right? Yeah,
And it's always going to work out.
it's always going to work out, right? Yeah. Yeah. Yeah, it's a question where usually I would think direct comparison test would be a good fit, but yeah, between direct conversion and limit conversion, hopefully we can kind of catch all the ones that that falls through the cracks. Okay, next page. Page 37. So we have absolute versus conditional convergence. Okay. So absolute convergence, there's 3 possibilities with regards to the series dealing with convergence or divergence. Now that we have alternating series in the mix, the idea of converging absolutely is if the absolute value of my rule of sequence converges, then the original series also converges. What that means is that if I can prove that without the alternator, my series can converge without the help of an alternator, then we say that the series converges absolutely. A conditional convergence is normally the series would diverge, but it converges with the help of alternator. Then we call that a conditional convergence because, and a good example of conditional convergence, what do you think is a good example of this? Yeah, 1 over n, right? This is a perfect example of conditional convergence because by itself, this would be a diverging harmonic series. But with an alternator, this all of a sudden converges because the limit of this rule of sequence does go to 0. Every term does decrease. So this is a conditional convergence. Okay. Divergent is if with or without the alternator, both series diverges. So this one we can just tell by nth term test. It's like, sometimes the alternator is not able to help because the nth term test of that rule of sequence diverges. So even with the alternator, it'll diverge. Yeah, so sorry, let's skip number one. We haven't talked about ratio test. So we'll come back to this one tomorrow. So this is a little bit out of order here, sorry. Yeah.
True, vice versa. I mean, not true vice versa, but if the one with the alternator diverges, then without the alternator would always diverge.
Say it again.
If you find that it would diverge with an alternator, it would always diverge without an alternator.
Yes, that's right. That's right. So so that is why for number 3 on the previous page, if we're able to just show that this series without the alternator doesn't go to 0, then we just say that the nth term diverges by, or the series diverges by nth term. We don't even care about the alternator because the rule of sequence is already failing the nth term test. Does that answer your question?
So the sum of any series with an alternator is always less than the same series without an alternator. Or no?
Yeah, the alternator potentially it will make a diverging series. It may not grow as fast as a diverging series without the alternator, but they're both gonna diverge. Yeah. So the big idea here is that if my rule of sequence doesn't go to 0, then I don't care about that alternator. It's not going to help enough to make it converge ever. Yeah, so sorry, number 1 is out of place. We'll skip that one. Let's look at number 2. So let's remove the alternator out of the equation and let's just look at this series here. I can rewrite this as what? 1 over n to the 1/3. What do you know? What do we know about this series? Yeah. I. So we know that this series diverges, right? But would it be able to converge with the help of the alternator? Does it pass the conditions for alternating series test? This equals to what? 0, right? And we can say that every subsequent term is decreasing. So we would say that this series converges conditionally because without the alternator, it would diverge, but with an alternator, it would converge. Yes. Any questions here? All right, number 3. first things first, let's just look at the rule of sequence without the alternator. What does this give us? What does that tell us?
It averages.
Yeah, diverges by n term. Sorry, just one, my bad. So the problem is ever asking about converging absolutely, conditionally, or divergent. We have three options, right? It'll converge absolutely if the series without the help of an alternator can converge on its own. It will converge conditionally if it diverges without the help of a alternator, but then all of a sudden converges with the help of an alternator. And the third option is if it fails the nth term test, we don't care what the alternator is doing. Okay, it'll fail with the alternator, it'll fail without the alternator. So nth term test. Okay, numbers 4 and 5 are out of place. This requires a ratio test. We'll come back to these tomorrow. So we'll come back to them. We're not going to do them just yet. Yeah, let me look. Yeah, anything with factorials, we don't know how to do that just yet. So if you see any factorials, you can go ahead and then skip those. Huh? Yeah. The factorials is the exclamation notation. Fourteen we can do. Okay, so let's get started on page 38. Okay, start with number 1, and I'll put the homework pages in a second here. I also included this in your calendar as well. So first, page 38 to 47, there are some problems with factorials, and you can skip those. And also on page 47, in the book, they split up 10.5 into alternating series test and the alternating error bound. We haven't talked about the error bound. We won't talk about that until after the quiz. So we'll come back to numbers 2, 3, and 5 on page 47, but we can skip those in the AP practice.
Yeah, I'm not sure you meant.
All right, let's keep working for another 5 minutes or so. Let's look at number one.
If you've got alternating series that have non-squared traits in the numerator, then would you expect it to fail that second condition sum?
If it is, let's see, numerator is what, non-squared?
If it's like, kind of like 7 on the.
Yeah,
thing.
yeah.
Does that trig function make it like alternate?
right. But it's gonna always kind of hover between like -1 and 1. So
Other than negative, or not be smaller.
that's right. That's right. Yeah, alternating series, every term has to be, the absolute value of every term has to be less than the previous one. So
Number 70.
number 7 is D, yeah. Yeah, that's a good point, where that first condition does pretty good, but then that second condition is a little tricky with that cosine.
6 like that too, the 6C.
6 is C, yeah, 1 and 3. Yeah, those are difficult instances. Yeah, we'll spend time going over them tomorrow. Those are, yeah. I guess, yeah, there's good examples of when each subsequent term is not quite always decreasing.
Did you look at number 12 too? Because
Yeah, number 12 is A.
so the limit of n approaches infinity of cosine n wouldn't exist, right?
It wouldn't exist, right? Because it's not approaching 0.
And so therefore the n term just it would diverge.
It'll diverge because it doesn't equal to 0. Even though it's hovering around 0, it is, yeah, it is still will diverge by nth term. Okay, so your homework pages 38 to 47, and tomorrow we'll go over our final test, which is ratio test, and then we'll start our quiz review Wednesday. Okay. All right, can we get your phones?